Ever wonder where your old laptop goes after you toss it out? Every single year, millions of tons of electronics like these end up getting recycled. But hey, it is not just trash. Inside, there is a real treasure trove. Gold, silver, copper. And right alongside that, toxic hazards, mercury, lead, and batteries just waiting to burst into flames at any moment. How do they protect your data on those old drives? Why are the workers dressed like astronauts? See for yourself the shocking but super important journey your old gadget takes, from the conveyor belt all the way to extracting precious metals. It is a sight that will totally change how you think about unwanted electronics. Keep watching. Specialized companies or collection points take in old laptops from regular folks and businesses. The devices get checked to see if they still work. Laptops that are still working might get fixed up and resold, or donated to charities. Large batches of laptops are transported to specialized facilities. There, trucks unload containers full of laptops. Workers using forklifts move them to the sorting area. Then, workers wearing protective gloves and special suits look over each laptop. Yeah, safety is a really big deal here. The people on the sorting line wear protective gloves and suits for a few reasons. Old laptops might have components containing lead, like in the solder, or mercury in the fluorescent backlights of the displays. Touching these without protection could lead to poisoning. Cadmium and beryllium are dangerous if they touch your skin, or if you breathe in the dust. These heavy metals are used in batteries and circuit boards. Some laptop parts, especially broken screens, can have sharp edges that could easily cut your hands. And during disassembly, small components can break off and go flying. Even when a laptop seems dead, some capacitors can still hold a residual charge. Touching them without protection could give you an electric shock. Special anti-static suits and gloves prevent damage to electronic components from static electricity. When the laptops are shredded, a lot of toxic dust is created, which can contain microscopic particles of metal and plastic. To avoid breathing this dust in, workers wear masks or respirators. Working laptop models are set aside during sorting. They can be repaired and sold. The rest are sent off for recycling. Lithium-ion batteries are removed by hand because they can catch fire or explode. During shredding, or if they get damaged mechanically, the battery can overheat and ignite. Lithium reacting with air or water can release flammable gases. Also, inside the battery, there are toxic electrolytes that can cause chemical burns or poisoning. If a battery gets deformed, these substances can leak out and get into the environment. That is why workers manually unscrew the panels and take out the batteries. If the battery is built in, they disconnect it using a special tool. The removed batteries are placed into heat-resistant containers filled with sand or other non-flammable materials. They are stored in well-ventilated areas, away from other waste materials. Recycling the batteries happens separately from the rest of the laptop. They go to specialized plants where the metal casings are shredded. From the internal materials, like nickel, cobalt, and lithium, useful components are extracted for reuse. After the batteries, the next critical step is removing the hard drives. Why are hard drives taken out separately? Well, the thing is, even if the laptop does not work, data can still be stored on the drive. And corporate or government laptops might contain sensitive data, so the hard drives have to be destroyed following special procedures. Some drives have moving mechanical parts, like platters and motors, which are processed separately. Other drives are made of memory chips that need a different recycling technology. Workers unscrew the laptop casings and remove the drives by hand. In some models, solid-state drives are built right into the motherboard. In that case, they are either desoldered or broken off along with the board. After that, there are 3 ways they physically destroy the drives to ensure data security. They are either shredded in special shredders, turning them into tiny metal fragments, or they are wiped using magnetic degaussers, which erases the data permanently, or they are melted down into metal ingots. The aluminum casings from hard disk drives are sent off for remelting. The magnetic platters have coatings of gold, platinum, and cobalt, which are extracted using chemical processes. Solid-state drive controllers contain copper, silver, and rare earth metals. These are also extracted for reuse. Once the batteries and hard drives are out, the laptops do not pose a serious fire or data security threat anymore. Now, they can be sent over for automated case disassembly. The laptops move along a conveyor belt, passing one by one under an automated press. Powerful hydraulic plates with up to 5 tons of force squeeze the casing, causing tiny cracks in the fasteners. One hit, and the top panel separates from the bottom, leaving the internal components accessible for further processing. The laptops keep moving down the line. Mechanical arms with thin metal fingers hover over them. Each arm is equipped with an automatic screwdriver unit that spins at up to 5,000 revolutions per minute. In just 4 to 6 seconds, the robot unscrews the screws and carefully removes the keyboard, speakers, and cooling system heatsinks. When the laptop reaches the next module, 2 pneumatic grippers grab onto the screen. A blade with a high-precision control system runs along the edges, cutting through the plastic fasteners. A barely audible crack, and the display is separated. Now the laptop is almost empty, with only the main guts left, the motherboard. Another arm removes it, using vacuum suction cups to lift the board and place it into a separate container. The whole process takes less than 2 minutes, and what was once a whole laptop is now just separate parts, ready for sorting and further recycling. The conveyor moves the separate laptop parts to sorting stations. Both robots and people work here. Plastic case panels are directed one way. They pass through special scanners that identify the type of plastic. Some types of plastic can be reused. Others are disposed of as regular waste or converted into fuel for industrial plants. Metal parts, like case frames, fasteners, and heat pipes, go through magnetic separators. Ferromagnetic metals, like iron and steel, are separated using powerful magnets. Non-ferromagnetic metals, like aluminum and copper, are sorted using induction detectors. Glass from the display screens goes into a shredder, where it is broken into small fragments. After that, special equipment cleans the glass granules of impurities. The resulting material can be used to make new displays or building materials. Motherboards, graphics chips, processors, and other integrated circuits are collected separately. They are checked to see if they can possibly be reused. If the circuits are still usable, they are sent to the secondary market or for refurbishment. Most electronic components, however, end up being recycled. To do this, they are sent to special furnaces where high temperatures burn off the organic materials. Only the metals remain: gold, silver, copper, palladium. They are extracted using chemical methods, purified, and returned to manufacturing. Laptops also contain hazardous substances: lead, mercury, cadmium, lithium. These cannot be allowed to enter the environment, so they undergo special processing. The fluorescent lamps from displays, which contain mercury, are separated under sealed conditions so that mercury vapor does not escape into the air. The recovered mercury is reused, for example, in medicine or in making thermometers. The lithium batteries, which were removed in the initial stage, are transported to separate plants. There, they are dismantled, and lithium and other useful elements are extracted. The resulting materials are used in the production of new batteries. Lead, found in solder, is melted down under controlled conditions, separating it from impurities. The entire process of dismantling, sorting, and recycling a laptop can take anywhere from a few hours to several days, depending on the scale of the facility and the technological process used. After sorting, all the materials are distributed into separate containers, or large industrial bins, depending on their type and the next steps in processing. In the plastic containers, you will find fragments of casings, keyboards, touchpads, which might be black, gray, or silver. The plastic is sorted by type: acrylonitrile butadiene styrene, polycarbonate, polypropylene. In the bins for metals, you can see piles of parts. Here lie aluminum frames and lids from laptop cases, copper heat sinks and wires, steel fasteners and screws. Containers for electronics are filled with the removed motherboards, graphics chips, random access memory modules. It all looks like a heap of complex green and blue boards with gold contacts and copper traces scattered across them. In separate containers for displays, there are dismantled screens with fragments of glass and metal frames. Sealed containers for hazardous materials hold batteries. Mercury lamps and capacitors containing lead are stored separately. These are often kept in special zones with warning signs about toxicity and explosion risks. After sorting, all these materials need to be transported to specialized plants where they will undergo further processing and preparation for reuse. To save space in trucks and containers, some materials are compressed. For example, plastic is shredded into granules or pressed into large bales. Metals are compressed into dense cubes. Glass is crushed and packed into bags or containers. Electronic components are stored in large containers without being compressed, since they still need to undergo chemical treatment. Lithium batteries are placed in special non-flammable containers, often filled with sand or expanded clay pellets to prevent ignition. Mercury lamps are transported in sealed boxes that prevent mercury vapors from getting into the air. The materials are loaded onto trucks, trains, or ships, depending on the distance and the type of material. Large metal cubes are lifted by forklifts and stacked in trucks. Containers with plastic and glass are transported in trailers or sea containers. Electronic components might be transported in special containers with shock-absorbing protection. Metals are sent to metallurgical plants, where they are melted down and purified. Aluminum, copper, and iron can be reused in manufacturing electronics, cars, or building materials. Plastic goes to plastics recycling plants, where it is shredded, melted down, and used to produce new casings for electronics, furniture, or packaging. Glass goes to facilities that manufacture new screens or building materials, for example, insulation made from recycled glass. Electronic circuit boards are delivered to plants specializing in extracting precious and rare earth metals. There, the integrated circuits are dissolved in chemical solutions to extract gold, silver, palladium, and other valuable metals. Batteries head to facilities where lithium, nickel, and cobalt are extracted for manufacturing new batteries. Hazardous waste goes to special landfills or chemical plants, where toxic substances are neutralized or rendered harmless under controlled conditions. After several months or even years, the materials from a recycled laptop can end up back in production, as part of a new device, building, or car. Some large recycling facilities specialize narrowly, for example, dealing only with computer equipment or mobile devices. Others recycle almost all types of electronics, including large household appliances. Every year, people throw out 4.4 billion pounds of washing machines. That is like 200 Eiffel Towers made of metal and plastic. But what if your old washer could snag you $200 from Samsung or LG, and then come back to life in a totally new way? In this video, we are going to show you how shredders rip steel apart in seconds, magnets snatch out copper, and plastic gets transformed into new gadgets. Why are brands willing to pay for your old junk? And how can a single machine either help save the planet or end up poisoning it? The first 30 seconds will spill a secret that is going to change the way you think about trash forever. You do not want to miss it. Lots of big brands and electronic stores have programs where you can trade in your old stuff, or they will haul away your old appliance for free when you purchase a new one. For instance, in the United States, companies like Whirlpool, LG, and Samsung have programs like this. Over in Europe, they have initiatives under the Waste Electrical and Electronic Equipment Directive. The details can be different depending on the company. Some will just haul away your old appliance, while others might give you a discount toward your new purchase. Whirlpool in the United States, for example, might offer anywhere from $50 to $100 off a new appliance if you're trading in an old washing machine. LG and Samsung sometimes run special promotions where they might offer $100 or even $200 back. Over in Europe, some programs might let you get up to a 10% discount on a new appliance. But more often than not, the discounts are not that big. Most companies really look at this as more of an environmental effort, not just a strategy to pull in customers. In a lot of cities, you will find electronic waste collection centers where people can drop off their old washing machines themselves. These centers often team up with local city governments or private recycling companies. In some countries, like Germany, the United Kingdom, and the United States, there are city-run services that will actually come and pick up bulky electronic appliances. For example, in New York City, you can schedule a free pickup through the city's own program called NYC Safe Disposal. There are also some companies that focus specifically on recycling metals. They might actually buy your old washing machine from you, or at least take it off your hands for free. These companies then send the appliances off to be taken apart, where they pull out all the valuable stuff like metal, electronics, and plastic. First things first, the machines get sorted into different groups. Ones that still work, ones that kind of work, and ones that are completely broken. The machines that still work might get fixed up and resold, but the ones that are too far gone head off to be taken apart. The teardown process starts by taking off the outside panels, the door, and the drum. Things like motors, electronic components, wiring, and pumps are separated out because they can often be reused as parts or melted down for their materials. The different types of metal get sorted separately, like stainless steel, aluminum, and copper. Plastic parts are also gathered up and sent off for recycling. This whole process can be done by hand, or it can happen on special automated lines where machines shred the main body and then use things like magnets and air separators to sort out the different materials. These automated recycling lines for washing machines usually involve several steps, and each step is designed to separate out specific types of materials. First, the washing machines are loaded onto a conveyor belt that feeds them into powerful rotating shredders. The blades on these shredders are strong enough to rip through the metal and plastic bodies, breaking them down into pieces roughly 1 to 4 inches across. Once everything is shredded up, the mix of materials moves past magnetic separators. These magnets grab onto any metals that are attracted to magnets, like steel and cast iron, pulling them away from all the other stuff. Next up is something called an eddy current separator. It uses a different kind of magnetic field to actually push away the non-ferrous metals, things like aluminum and copper. Plastics and other lightweight materials get separated out using air separators. Basically, strong blasts of air blow the lighter bits, like plastic flakes, upwards and into collection bins, while the heavier stuff stays put on the conveyor belt. Toward the end of the sorting line, whatever materials are left might go through optical scanners. These scanners can analyze what the pieces are made of and sort them even further, sending them to the right place for more processing or final disposal. So, after all this sorting with air separators and optical scanners, the different materials head off to their own separate processing lines. This is where the plastic, metal, glass, and anything else gets processed so it can be reused or recycled properly. The leftover metal pieces, like the steel parts, are shipped off to metal processing plants. There, they get melted down and eventually used to make brand new products. Remember those magnetic separators? They are super effective at pulling out iron and steel, which then get sent off to be melted down. The plastic parts get shredded into smaller pieces and then usually compressed into dense bales or blocks. These bales can then be shipped to specialized factories where they will be used to make new plastic items, or they might become part of the raw material mix for new appliances or other tech gadgets. If the washing machine had any glass parts, maybe in the door window, that glass gets cleaned really well to remove any gunk, and then it can be melted down to make new glass products. Any leftover materials that cannot really be recycled, maybe certain kinds of rubber or complex mixtures of stuff, usually end up getting sent for final disposal, often meaning they go to specially designed landfills. These kinds of sorting and recycling setups drastically cut down on the amount of waste that just gets dumped in landfills. Plus, they help get valuable raw materials back into the economy so they can be used again. Sometimes, especially for really tricky materials, they have to use more advanced techniques, like thermal decomposition, which uses heat or special chemical treatments. These methods come into play for stuff that is hard to separate just by shredding and sorting mechanically, or for materials that need extra processing to make sure they do not cause pollution or release harmful substances. Good examples are certain plastic components that have other materials embedded in them, like plastic with metal pieces fused inside or attached rubber seals. Materials like these often cannot be sorted easily using the standard methods, so they need special treatment to break them down and separate the different parts. Rubber parts, particularly those made with complex chemical additives, are often tough to recycle effectively because of their complicated structure. For materials like that, processes like thermal decomposition or other chemical methods might be used. The goal is to basically unzip them into simpler building blocks that can potentially be reused or at least disposed of more safely. In situations where the appliance contains hazardous stuff, think mercury in old switches, or maybe some types of batteries or old lighting components, those materials absolutely have to be handled with special procedures. This might involve a chemical process designed to neutralize the dangerous parts, or maybe one that locks them up safely so they can be disposed of without causing harm. Materials like polyurethane or polyester, which you often find used as insulation around wires or in various other parts inside appliances, might also be treated with thermal decomposition. This helps break them down into simpler substances that could potentially be recycled. And then you have situations where washing machines or other electronics contain complex composite materials. Stuff made of several layers of different materials bonded together, like plastic fused with metal layers or reinforced with fibers. These often require very specialized processing to carefully separate the layers so that each material can hopefully be recycled on its own. Overall, the reason for using all these different technologies is to make the whole disposal process as efficient as possible and to minimize the harm done to the environment. Because if these materials are not handled the right way, you could end up with pollution or dangerous chemicals leaking out into the ground or water. Did you know that your old air conditioner could poison the soil, wreck the ozone layer, and even cost you thousands of dollars in fines? Every single year, Americans throw out millions of air conditioners, and each one is a ticking time bomb of toxic chemicals, heavy metals, and dangerous gases. In this video, I'm going to show you how they actually get recycled. Freon, copper, mercury, nothing gets spared. And trust me, this affects all of us. So first things first, why should anyone bother recycling an air conditioner the right way? To answer that, let's break down what's actually inside one of these machines. Air conditioners contain refrigerants. These are chemicals that can do serious damage to the atmosphere. Older units use ones that destroy the ozone layer. Newer ones, they may not harm the ozone, but they still contribute to global warming. The internal boards and compressors are loaded with toxic stuff like lead, mercury, and cadmium. If you just dump an old AC in a landfill, all that junk can leak out into the ground and water. Now, compressors also contain valuable metals like copper, aluminum, and steel. Those can be reused, cutting down the need to mine more raw materials. But here's the kicker. If you try to tear one of these apart without the right safety measures, those toxic materials can leak out, fast. That's why so many countries, including the United States, have strict environmental laws banning improper disposal. And yeah, in some cases, those fines are no joke. In the United States, old air conditioner disposal is regulated on a federal level by the Environmental Protection Agency, plus individual state rules on top of that. Now, we've already touched on how long these machines usually last. So let's dive deeper. Window and portable units typically last from 8 to 10 years. Split systems? They give you a few more. And those big centralized setups, yeah, the ones we mentioned earlier, they'll run for about 15 to 20 years. Keeping filters clean, topping off refrigerants, and doing regular checkups can stretch that lifespan. But in hot areas where ACs run all summer long, they tend to wear out faster. Once your system hits the end of its life, it loses efficiency. Your power bill goes up and repairs become a money pit. That's why most people end up replacing them, which means more units headed for recycling. There are several ways to recycle air conditioners in the US. A bunch of utility companies run take-back programs for old ACs. Some even offer cash, anywhere from $25 to $100. just for handing your unit over. All you gotta do is apply, and a technician comes out to pick it up and handle it properly. Big chains like Best Buy, Home Depot, and Lowe's will take your old AC for recycling too. Some states have dedicated drop-off sites for electronic waste where you can bring in your unit for free or a small fee. In many cities, there are special bulky item collection days. And some towns offer curbside pickup of old appliances, sometimes even for free if you book ahead. Even charities like Habitat for Humanity Restore take working ACs to resell or use in community programs. And a lot of stores have trade-in deals, where you bring your old one in and get a discount on a new model. When we're talking about centralized systems though, you can't just yank one out yourself. You need to call a licensed tech. They'll recover the leftover refrigerant using special equipment, then ship the whole system off for proper disposal. In many states, improper disposal can mean fines, from $100 to $500 on average. But in some cases, it can climb into the thousands. Bottom line, either take your unit to a recycling facility or use one of those special programs. That's the smart move. Once the AC arrives at the facility, the first step is a professional teardown to safely remove hazardous materials and prep everything for recycling. Removing Freon is a whole process that needs special tools designed to safely extract it from the system. The technician hooks up a refrigerant recovery machine to the AC's tubing system. This device uses vacuum pumps and pressure gauges to control the flow. The system gets opened through service valves, giving access to the Freon lines. The vacuum pump slowly pulls the refrigerant out and transfers it into a sealed recovery cylinder. The tech keeps an eye on the gauges to monitor pressure and make sure every last drop is extracted. Depending on the unit size and how much refrigerant is inside, this process can take anywhere from a few minutes to half an hour. During this step, the workers are fully suited up because contact with refrigerants can be harmful. The equipment's built to prevent any leaks. Everything happens in a sealed environment. Once the Freon is removed, it's stored in that sealed tank and later handed off to certified hazardous waste recyclers. With the refrigerant safely gone, the unit moves on to the disassembly phase, which is crucial for proper recycling. The techs set up special workstations at the facility. Before disassembly starts, they review the paperwork and lay out a plan so they know exactly which parts to pull and how to sort them. The AC gets broken down into its core parts: the outer casing, compressor, heat exchanger, fan, electronics, piping, and smaller components. A typical unit has around 20 to 30 different pieces. The compressor alone might weigh between 30 and 50 pounds. Radiators, anywhere from 20 to 40 pounds each. They use both hand tools and machines, like hydraulic lifts and electric grinders, to cut or unbolt the big metal parts. This step takes about 30 minutes to 2 hours per unit, depending on size and complexity. Once everything's apart, the pieces are sorted by material: metal, plastic, and electronics. Around 90% of the metal in an old AC can be recycled. Metal gets cleaned of paint and grease, then sent for smelting and reuse. Plastics go to specialized recycling plants. Electronics that contain dangerous stuff, like lead and cadmium, are sent to e-waste recycling centers. On average, just one unit can provide 5 to 15 pounds of recyclable metal. That's a big deal when it comes to saving raw resources. Many recycling centers handle tens of thousands of air conditioners every year. That keeps a massive amount of toxic waste out of landfills. After the unit's fully disassembled, the next key step is sorting and prepping the materials for reuse. This process helps maximize resource recovery and shrink the environmental impact. After the initial cleaning, materials are sorted by quality standards. Metals get split into categories: aluminum alloys, steel, and copper. For example, copper wiring is often separated because its market value sits around $4 to $5 per pound. Plastic waste is grouped by type. The bundles for recycling usually weigh between 5 and 20 pounds. Electronic components are sorted by type: motherboards, capacitors, batteries. So recyclers know which ones need special handling, especially those containing rare metals. After sorting, all materials are packed up for transport. Metal parts go into containers headed for smelters. A single container can hold anywhere from 500 to 1,000 pounds of metal. Plastic granules are bagged or boxed up, usually in 50 to 100 pound batches, ideal for manufacturing. Electronics are shipped to specialized facilities where they get broken down even further. Thanks to this whole process, a single air conditioner can yield a surprising amount of reusable material. Recycling and disposing of A to C the right way also saves energy. Smelting recycled metal takes about 60% less energy than making new metal from raw ore. And today, some companies are already rolling out tech to automate disassembly and sorting, making the whole system more efficient and less dependent on human labor. Every day in the United States, folks toss out 27,000 microwave ovens. That's nearly 2.5 million a year. But what happens to them once they're kaput? You'll be shocked at how wild the recycling process gets. From tearing apart transformers packed with hazardous stuff to digging out gold from circuit boards, every step is a jaw-dropper. How do factories handle hundreds of tons of metal daily? Why do magnetrons need special treatment? And what's the deal with the plastic parts? Stick around to the end to uncover the secrets of e-waste recycling. Recycling microwave ovens in the United States of America is a tricky business, involving a bunch of steps, all geared toward cutting down environmental harm and squeezing every bit of reusable material out of them. It all kicks off with properly disposing of the oven according to local rules and laws. Tons of towns have special e-waste drop-off spots where people can hand over their old appliances. Plus, big retail chains and microwave makers often run take-back programs, sometimes even tossing in discounts on new buys as a sweet deal. Once the thing lands at a recycling center, the first move is breaking it down and sorting out the main parts. This happens at specialized e-waste recycling hubs or appliance recycling plants. These places are scattered across the United States, mostly clustered in industrial zones or near big cities where electronic junk piles up fast. Some are private outfits, while others roll under city-run recycling efforts. First off, workers figure out if the oven can be reused or if it's headed for a full teardown. If the microwave's in rough shape, it goes straight to the disassembly line. They start by yanking off the outer shell, usually made of steel or aluminum. Breaking down microwave ovens can happen by hand or with machines. In smaller recycling spots, most of the work's done manually with basic tools like electric screwdrivers, pliers, hydraulic shears, and teardown stations. They unscrew the outer metal panels first, popping open access to the guts inside. Workers pull out the big pieces, like the magnetron, transformer, circuit boards, and wiring. The metal bits get squashed and shipped off to steel mills, where they're melted down for reuse. Inside every microwave is a magnetron, the thing that pumps out those microwaves. It's got ceramic insulators, copper coils, and a tiny bit of toxic stuff, like beryllium. Since beryllium dust can be nasty, magnetrons get handled with care, using protective gear and special recycling tricks. At big industrial recycling centers, they roll out automated teardown lines. A key player here is the electronic shredder. Think machines like the hammer mill or SSI dual shear, stretching 15 to 20 feet long and chewing through hundreds of microwaves an hour. After shredding, the materials hit magnetic separators, which pull steel apart from the rest. At heavy-duty plants, teardown's a multi-step gig with fancy machines. For transformers, they use hydraulic cracking presses to bust open the casing and get at the copper or aluminum windings. To snag precious metals from circuit boards, they dunk them in chemical baths or fire them up in furnaces at over 2,000 degrees Fahrenheit to melt out the good stuff. On average, big plants can rip apart 500 to 1,000 microwave ovens a day, depending on how much gear comes in and how automated they are. At smaller outfits, where it's mostly handwork, they process 50 to 200 units daily. Next, they yank out the circuit boards, loaded with resistors, capacitors, and microchips. These get handed off to companies that extract precious metals like gold, silver, and palladium. The copper wiring inside gets peeled out and recycled too. While exact numbers on precious metals from microwaves in the United States are hard to pin down, e-waste recycling overall brings a hefty haul of valuable materials back into the game. Another big piece is the high-voltage transformer, made of a metal core and copper or aluminum windings. Since it's got insulation that could be risky, recycling it takes some extra steps. The main hassle with transformers is their density and toughness, making it a chore to pull out the materials fast. Teardown starts by prying the transformer loose from the microwave's shell. This happens manually or with electric screwdrivers and teardown stations. Then it's hauled to the recycling zone. If it's by hand, workers use hydraulic shears, grinders, or metal cutting presses to slice open the outer casing. The transformer's core, usually layered steel, needs serious muscle to split, so big plants lean on industrial shredders or hydraulic presses. One slick way to crack transformers is with special crushing presses that smash the casing, letting workers fish out the insides. After that, the copper or aluminum windings get peeled off the core and sent for melting. Magnetic separators sort out the steel from the rest. Shredded bits ride a conveyor belt, and as they pass under a magnet, ferromagnetic stuff, like steel plates and transformer cores, sticks to it, then drops into a separate bin. Another type, the drum magnetic separator, uses a spinning magnetic drum. Shredded materials roll onto it, and magnetic force grabs the iron bits, spinning them along until they fall off into their own container once they're out of the magnetic zone. Beyond the mechanical approach, some plants use heat to break down insulation. Transformers get roasted in special furnaces at 1,000 to 2,000 degrees Fahrenheit to burn off organic junk and free up the metals. In some cases, they go with chemical leaching, soaking the transformer in acid, or alkaline baths to dissolve certain parts. Extra caution's needed with the insulation, since it might hold toxic stuff. Older models, for instance, used varnishes with polychlorinated biphenyls, nasty chemicals. So recycling those means wearing protective gear and sending the waste to special hazardous material plants. One slick way to crack transformers is with special crushing presses that smash the casing, letting workers fish out the insides. After that, the copper or aluminum windings get peeled off the core and sent for melting. Magnetic separators sort out the steel from the rest. Shredded bits ride a conveyor belt, and as they pass under a magnet, ferromagnetic stuff, like steel plates and transformer cores, sticks to it, then drops into a separate bin. Another type, the drum magnetic separator, uses a spinning magnetic drum. Shredded materials roll onto it, and magnetic force grabs the iron bits, spinning them along until they fall off into their own container once they're out of the magnetic zone. According to the United States Environmental Protection Agency, about 25% of e-waste, including microwave ovens, gets recycled. Every day, around 27,000 microwaves get retired across the United States, adding up to roughly 2.5 million a year. Recycling cuts down on landfill clutter, helping keep soil and water free of toxic leaks from electronic gear. Properly handling hazardous parts, like capacitors or insulation, stops harmful stuff from hitting the environment, which is a win for people's health and ecosystems. 850 horsepower. That is the power output of the hybrid Lamborghini Revuelto. This is almost like having the force of 2 average tanks. Whenever you see a Lamborghini on the road, it is impossible not to turn your head. This is a car that shouts success and style, and it does so very loudly, thanks to its V12 engine. A Lamborghini is not merely an automobile. It is a symbol of status, luxury, and wildly high speed. However, this car is not just beautiful. Its heart is a genuine masterpiece of engineering. Shall I tell you about the engine? Lamborghini is renowned for its naturally aspirated engines that roar like a wild beast. The brand's most famous motors are the legendary V10 and V12, which provide not only insane power, but also an incredible sound that sends chills down your spine. The V12 engine was already present in the first Lamborghini 350 GT from the year 1963, and it remains the company's signature to this day. The establishment of Lamborghini was not merely a business project, it was an act of revenge. In the small town of Sant'Agata Bolognese, under the blazing sun of Emilia-Romagna, a company was born that challenged none other than Ferrari. Ferruccio Lamborghini was a successful businessman who became wealthy through the production of tractors. He owned an entire collection of sports cars, but he had problems with the Ferrari 250 GT because its clutch often broke down. One day, Lamborghini decided to express his dissatisfaction directly to Enzo Ferrari. He proposed improving the cars, but he was met with this response. "Ferruccio, you are just a farmer. You should focus on tractors and stay out of sports cars." Those words were the point of no return. Lamborghini resolved to build his own supercar that would surpass Ferrari. He hired the best engineers, including Giotto Bizzarini, the person who had developed engines for Ferrari. The team created that same legendary engine that became the heart of the first Lamborghini 350 GT. Even then, the car showed that Lamborghini was not joking around. It was faster and more comfortable than Ferrari. The first car was a success, and the company began to grow rapidly. Within only a few years came the legendary Misura, then the Countach, the Diablo, the Murcielago, and the Aventador. And now, for 60 years, Lamborghini has continued to be a symbol of status, aggression, and an engine's ferocious roar. The main Lamborghini factory covers 1,743,752 square feet. That is nearly the size of 23 soccer fields. This place is a genuine temple of speed and engineering artistry. All the critical steps in creating supercars are concentrated here. Massive pavilions equipped with ultra-modern technology merge with the craftsmanship of hand assembly, which remains an unchanging tradition of the brand. The factory includes a materials laboratory where carbon fiber is tested, paint booths where each automobile receives a perfect finish, and the exclusive ad personam division that allows clients to customize their Lamborghinis down to the finest detail. Every vehicle undergoes strict quality tests before leaving this temple of speed, bound for owners all over the world. In the year 2023, Lamborghini set a production record for the entire history of the company. 8,405 brand new cars rolled off the factory line. Every contour of the body is designed not only for aerodynamics, but also for maximum visual impact. The low profile, the aggressive front end, the sharp edges, and the massive air intakes all form the image of a wild predator ready to pounce. The signature guillotine doors on the Aventador or Revuelto models are an unforgettable sight. They lift upward. The moment you open them, you already look like a movie star. Buying a Lamborghini is not simply about money. It is about a way of life. Lamborghini owners want to stand out, be at the center of attention, and experience an adrenaline surge each time they press the gas pedal. It is no surprise that among these owners are soccer players, actors, business people, and even princes. Lamborghini has always been synonymous with exclusivity. Production is limited. Most models are released in small batches, and some appear in limited runs of 10 or 20 units. For example, the Lamborghini Centenario was produced in only 40 units, 20 coupes, and 20 roadsters. Lamborghini uses only premium materials, most of which come from the world's top suppliers. The main material is carbon fiber. Did you assume the body was made of metal? It is not. Carbon fiber is an ultra-strong yet lightweight material made up of extremely thin strands of carbon, each roughly 10 times thinner than a human hair. It is stronger than steel, but weighs several times less, making it ideal for supercars. Carbon fiber begins with polyacrylonitrile threads, which are a synthetic material similar to plastic. The fibers are heated in special furnaces with oxygen, which alters their chemical structure and makes them thermally stable. Then the fibers move into furnaces without oxygen, for instance in a nitrogen atmosphere. Under extreme temperature, they lose all inorganic components and are left as nearly pure carbon. These carbon threads are then treated to bond more effectively with polymer resins. The finished fibers are woven into fabric or laid out as ribbons. The carbon fabric is infused with resin and then shaped as needed. Lamborghini uses forged composites technology, where the fibers are arranged randomly, resulting in parts that are even lighter and stronger. The form goes into a high-temperature, high-pressure autoclave, where the composite hardens and gains extraordinary rigidity. Imagine strands thinner than a hair passing through furnaces at 3,632 degrees Fahrenheit. What comes out is a black thread that is 5 times stronger than steel, yet 7 times lighter. Instead of a conventional steel component weighing 33 pounds, Lamborghini gets a carbon substitute that weighs 6 pounds, while preserving the same strength. This material enables Lamborghini to craft bodies that are light, strong, and fast, reducing the vehicle's overall mass and boosting its aerodynamics and performance. Aluminum is sourced in Europe, especially from Italy and Germany. It is utilized for fabricating the chassis, the load-bearing body components, and various structural parts, since it is both light and strong. Suppliers deliver aluminum as sheets, profiles, or ingots. When it arrives as ingots, it is melted down and cast into blanks. Aluminum is melted in special furnaces at around 2,232 degrees Fahrenheit. The molten metal is poured into molds under high pressure. The casting solidifies in a matter of seconds and is then removed. The cast pieces are ground, excess material is trimmed off, and they undergo heat treatment to enhance their strength. Using aluminum makes the frame about 40% lighter than a steel alternative. Lamborghini's press machines can produce up to about 11,000 short tons of forming pressure. A single aluminum Aventador frame weighs a mere 504 pounds, which is essential for high speeds and maneuverability. Natural Italian leather arrives from renowned tanneries in Tuscany and Piedmont. Alcantara is sourced from a factory in Umbria for the upholstery. Carbon inserts are produced directly at Lamborghini. It may require 7 or even 8 cowhides to upholster the interior of one Lamborghini. Buyers can choose any color of leather via the ad personam personalization program. Lamborghini uses premium Napa leather and aniline leather, which both have a natural texture and softness. All leather sections are handcrafted to maintain exclusivity. The leather is manually cut for each part to avoid defects or unevenness. Every seam is also stitched by hand, ensuring precise quality control. Special leather threads are used for this purpose. Each piece is dyed and treated to achieve the requested appearance and texture, consistent with the client's wishes. Once every piece is ready, it is assembled and installed in the automobile. Alcantara is a high-end synthetic material that resembles suede in both look and feel. It is widely applied in the automotive sector. Alcantara is soft, matte, and holds up better to wear than genuine leather. It is also twice as light as leather, which is critical for supercars. It does not fade, retaining its color even under direct sunlight, and it is made of 68% recycled materials. The assembly process begins with preparing the vehicle body and chassis. This involves installing a foundation constructed from lightweight metals or carbon fiber, depending on the specific model. At this stage, every mainframe element is brought together, including the suspension, the exhaust system, and other key components. This step is of the utmost importance, as it lays the groundwork for everything that comes afterward. The body is assembled by hand, using specialized tools and fixtures to ensure maximum precision and minimal gaps. Once the body and chassis are complete, the next step is the installation of the engine and the transmission. The engine is the heart of a Lamborghini, and putting it in place is an exceptionally intricate process. All Lamborghini engines are built and tested separately prior to being mounted in the car. Installing the engine also requires connecting it to the cooling system, the exhaust, and the vehicle's electronics. After this, the gearbox and the transmission system are fitted, allowing the engine's power to be transferred to the wheels. During this phase, all of the vehicle's critical systems are also fine-tuned, including the suspension and braking systems. The following stage involves installing the car's interior parts. This includes the seats, the instrument panels, the door trim, and the steering wheel. All these elements are made by hand using superior quality leather or Alcantara, in the case of sportier versions, along with other exclusive materials. Every piece is finished with meticulous attention to detail, creating a truly unique cabin. For instance, Lamborghini seats are crafted by hand to accommodate every curve of both driver and passenger, providing outstanding comfort. The steering wheel is also handmade and can feature a personalized design, according to the client's preferences. Once the principal interior components are set, the car moves on to the phase dedicated to connecting the electronic systems. Lamborghini cars are noted for their cutting-edge technology, so they come equipped with intricate infotainment setups, navigation, touchscreens, and safety systems. All wires and electronic parts must be hooked up with extreme accuracy to avoid errors or malfunctions. This process can take several hours and calls for highly qualified technicians who precisely follow each component's wiring diagrams. Having finished the physical assembly of the automobile, Lamborghini proceeds with the testing stage. Each vehicle goes through a detailed evaluation on special test stands, where every function and system is checked, ranging from the engine and transmission to the brakes and suspension. This helps detect any faults or issues before the car reaches the end buyer. One of the most vital segments of testing is assessing the car's performance dynamics on the track. Here, the automobile's characteristics at high speeds are evaluated, along with its maneuverability, braking force, and stability when cornering and accelerating. Once all tests have been completed, the car returns to the assembly hall for a final inspection. If all systems operate correctly, the vehicle undergoes one last quality assessment. After this, it receives finishing touches, such as body polishing and a thorough check of every surface for paint defects. At Lamborghini, each car has its own special color, chosen during the production phase. After this, it receives finishing touches, such as body polishing and a thorough check of every surface for paint defects. At Lamborghini, each car has its own special color, chosen during the production phase. Every minute, more than 55 short tons of whey protein are produced worldwide. But just a few decades ago, people would simply pour out this liquid, not realizing it held one of the purest sources of protein. Today, it is a multi-billion-dollar industry where ordinary whey from milk undergoes a high-tech journey of filtration, drying, and packaging before ending up in your sports shake. How did this ordinary byproduct of the dairy industry become the foundation of sports nutrition? Let us figure it out. The cycle begins with choosing high-quality raw materials. Do you know what whey is, if we are not talking about vaccines? When milk is used to make cheese or yogurt, it separates into two parts: the solid curd that becomes cheese, and the liquid whey, which was thrown away or used as animal feed several decades ago. However, people discovered that this liquid is full of valuable proteins, so it is now filtered, dried, and transformed into powder, the same whey protein you find on store shelves. When milk curdles, only 10 or 20% of it turns into cheese, while the remaining 80 or 90% is whey. Most large protein producers work directly with farms located near their factories to secure a steady supply of this raw material. In the United States of America and Europe, whey often comes from large dairy farms. In Australia and New Zealand, it is commonly sourced from traditional pasture-based farms, where cows eat natural grass. The quality of the protein depends on the quality of the milk, and that quality is influenced by how cows are raised. This is why some brands emphasize that their whey protein is from grass-fed cows, without antibiotics or hormones, and from certified dairy farms. The type of final product also depends on the milk's fat content. If the milk is used to produce a full-fat cheese, such as cheddar or Gouda, the resulting whey has less fat and is more suitable for making a pure protein powder. If it is a lower fat cheese or cultured dairy product, the whey may contain more lactose, which affects the flavor and overall quality of the final powder. Many whey protein manufacturers prefer whey from hard cheeses because it typically has a higher concentration of pure protein and fewer byproducts. To make about 2 pounds of cheese, you need approximately 2 1/2 gallons of milk, and the rest of that milk turns into liquid whey, which can be used to obtain protein. Whey protein naturally contains very little fat, since most of the fat stays in the cheese. The whey that will be turned into protein is transported to factories in special sealed containers or tankers. Because whey is a liquid that spoils quickly, it must be delivered at low temperatures to maintain its quality. Once whey is collected from the milk, it is cooled to around 39 degrees Fahrenheit to reduce the risk of bacterial growth. For transport, specialized insulated tankers or trucks with refrigerated compartments are used. These vehicles can maintain a constant temperature to keep the whey fresh during the trip. Transport containers are typically airtight to prevent air from spoiling the whey and to preserve its quality. After delivery, the whey is usually tested to ensure it meets the standards required for further processing into protein. This transport system guarantees that the whey arrives at the factory with its beneficial properties intact and is ready for the next steps of protein powder production. Once the whey reaches the plant, it is carefully transferred from the tankers into large, specialized reservoirs. These are often stainless steel vats or other containers that keep the liquid hygienic. If the whey has not yet been cooled to the ideal temperature, it undergoes additional chilling to prevent bacterial growth and to provide optimal conditions for the next manufacturing stages. At this stage, the whey may pass through filters to remove any foreign particles or unwanted impurities. This step is crucial to avoid quality issues later in the protein production process. Often, the whey is first concentrated by removing some of the water through ultrafiltration or other techniques, which increases the protein content. In certain cases, the whey may be heated to activate specific enzymes or prepare it for subsequent processes, thereby improving the efficiency of protein extraction. Protein, also called a protein molecule, is an organic compound composed of amino acids linked by peptide bonds. It is a major building block of the cells in living organisms and performs numerous vital functions within the body. Proteins play a key role in forming tissues, cells, and organs, as well as in driving various processes essential for an organism's life activities. They are the main components of cells and tissues. Proteins create structures like muscles, skin, hair, nails, organs, and other tissues. Many enzymes are proteins that speed up chemical reactions in the body, including food breakdown, energy production, and other important biochemical functions. Proteins are involved in the transport of molecules and ions in the body, such as hemoglobin, which carries oxygen in the blood. They also regulate various biological processes, including growth and development, and support the body's immune defenses in the form of antibodies. Although supplying energy is not the primary role of protein, the body can use it as an energy source when necessary, especially if carbohydrates and fats are in short supply. Proteins consist of 20 main amino acids, 9 of which are essential, meaning the human body cannot produce them, and they must come from food. Animal products like meat, fish, milk, and eggs contain all the essential amino acids, making them complete protein sources. Membrane filtration is a critical step in processing whey for protein powder production. It allows an efficient separation of the beneficial protein from less useful components, such as lactose, fats, and minerals. This procedure employs special filtration membranes with microscopic pores, functioning like extremely fine sieves that only allow molecules of certain sizes, including proteins, to pass through. 3 main types of membranes are typically used for membrane filtration: ultrafiltration, nanofiltration, and reverse osmosis. In the first stage, membranes with larger pores let water, lactose, and minerals pass through while holding back larger protein molecules. Nanofiltration membranes have smaller pores, allowing only smaller molecules such as minerals to pass while retaining bigger protein molecules. The final step, often referred to simply as osmosis in a reverse osmosis system, helps remove water and small molecules like lactose, resulting in a concentrated protein. Once the whey enters the membrane system, it is pushed through the membranes under pressure. The portion of the liquid that contains dissolved substances such as water, lactose, and minerals passes through the membrane, while larger protein molecules remain on the membrane's surface. This approach yields a more concentrated protein. After membrane filtration, the whey is divided into two streams. One contains the larger protein molecules, the concentrated protein, which will be further refined into protein powder. The other includes lactose, minerals, and water, and may be discarded or used for other food or industrial purposes. This process can be repeated multiple times to further boost protein concentration, resulting in protein concentrate or protein isolate, which differ in their levels of purity. Following membrane filtration, once the whey has reached a high protein concentration, the next step is drying. This is crucial because it transforms the liquid concentrate into a powdered form that is easy to store, transport, and use. One of the most widespread methods involves exposing the whey concentrate to a stream of heated air, which evaporates the moisture and leaves behind powder. This approach is sometimes referred to as hot air drying, or a form of air-based microfiltration, and it is commonly used to produce powders with a high protein content. In the case of rotary dryers, the whey concentrate is dispensed onto rapidly rotating drums heated by hot air, causing the moisture to evaporate. Another frequently used technique is spray drying, where the whey is sprayed into fine droplets in a chamber that circulates hot air. The droplets quickly lose moisture, forming small particles of powder that readily dissolve in water. During drying, it is crucial to control the temperature, because very high temperatures could damage protein molecules or compromise the final product's quality. Typically, the temperature does not exceed 175 degrees Fahrenheit in order to retain all of the protein's beneficial properties. After this step, the whey becomes a powder with a moisture content of less than 5%. The powder is then stored in sealed packages to prevent it from absorbing moisture from the air. That is all there is to it. The only remaining task is to package the finished protein. Modern factories use high-speed packaging lines. For example, a single automated line can fill up to 40 packages per minute. Over one day, it can pack around 50,000 packages of protein powder, which usually totals 2 or 3 short tons of finished product. The packaging process is completely automated. Powder travels directly from a container or hopper into packaging machines that automatically fill each package with gram-level accuracy, ensuring precise dosing. Packaging machines operate not only at high speed, but also with great precision. They can include sealed closure systems to prevent air and moisture from entering, which helps the product remain fresh. An automated system inspects every package to detect any defects, such as incomplete sealing, and discards flawed packages. Once the protein powder is packed, the packages may be automatically marked, labeled, and moved onto a conveyor for further boxing or palletizing for shipment. These machines are capable of packing up to 1,000 packages per hour into a single box, guaranteeing rapid and efficient delivery of the final product to consumers around the world. Every year, more than 12 million cars are scrapped worldwide, and this has become a massive industry running like clockwork. Imagine this. Your old ride could turn into a brand new skyscraper, and that worn-out engine might end up in a military battleship. But what actually happens to cars that have reached the end of the road? They are not simply tossed away. 90% of their materials get recycled. How are cars dismantled, crushed, and literally torn apart to be turned into something new? Today, we are taking a deep dive into this process. Why can you not just leave your old car sitting in the backyard? Well, first of all, it is illegal. Unless you live somewhere where keeping a car on bricks in your yard is completely fine. Second, old cars leak fluids, motor oil, antifreeze, transmission fluid, that can seriously damage the environment. Third, they take up space that could be used for something better, like a new car or even a barbecue grill. So, what are your options? If your car is still somewhat functional, you can sell it for parts. Even if the engine is done for, many components still have value. The battery, if it is still working, can be sold separately or taken to a recycling center. Tires, if the tread is still decent, can be resold. The catalytic converter contains precious metals like platinum, palladium, and rhodium, making it highly valuable. Headlights, mirrors, doors, there is always someone looking for replacement parts. You can sell them on Facebook Marketplace, Craigslist, or local auto shops that buy used parts. If your car is so far gone that even a tow truck refuses to take it, scrapping it for metal is the way to go. On average, scrap metal prices range from $100 to $300 per 2,000 pounds, meaning a regular sedan could get you anywhere from $200 to $600. Before dropping it off, make sure you have the proper paperwork, remove all personal belongings from the interior, and if possible, drain the fluids. Many scrapyards will pick up the car themselves, especially if it is undrivable. How about donating it to charity? In the United States, plenty of organizations accept cars as donations, even if they are not running. Some examples include Cars for Kids, Goodwill car donations, and Wheels for Wishes. You just make a call, they tow it away, and you get a tax deduction. Plus, it feels good knowing your old clunker is helping someone in need. From time to time, government programs allow you to trade in an old vehicle for compensation. In California, for instance, the Consumer Assistance Program offers up to $1,500 for cars that fail to meet environmental standards. It is worth checking if similar programs exist in your state because this might be the most profitable option. Do not leave your car abandoned on the street. That could result in fines or impoundment. Do not try to dismantle it yourself unless you know what you are doing. Some parts, like the fuel tank or battery, can be hazardous. And do not confuse proper recycling with illegal sales. Many states have strict regulations about selling non-operational vehicles without the right documentation. The key is doing it correctly to avoid trouble and protect the environment. In movies, we often see massive junkyards filled with rusting cars under the scorching sun. In reality, most vehicles do not just sit there. Modern recycling is a well-organized process where nearly 90% of materials get repurposed. If a car is beyond repair, it moves on to the dismantling stage. You already know about the initial teardown. After that, the car goes into a hydraulic press, the same machine you have probably seen in movies. It compresses the car into a compact cube, reducing its size by several times. These crushed cars are then sent to massive industrial shredders, huge machines that literally rip the car apart. After that, the shredded metal and plastic move on to sorting. Sorting is done using magnetic separators, which separate metals. Steel and iron are the easiest to extract since they are attracted to magnets. Aluminum, copper, and brass are removed using eddy currents and other techniques. Plastics, glass, and rubber are collected separately, although not everything can be recycled. Once sorted, the materials go to specialized recycling plants. Steel and aluminum are melted down and used to manufacture new cars, construction materials, household appliances, and more. Wheel rims and engine blocks are often turned into new auto parts. Components like bumpers, dashboards, and interior panels are shredded and reused for making furniture, insulation, or even new cars. Automotive glass contains a plastic layer inside, making it harder to recycle, but some companies repurpose it into construction materials. Tires do not decompose and are an environmental hazard, so they are repurposed as much as possible. They are turned into asphalt granules, rubber flooring for playgrounds, and even fuel for cement plants. 99% of car batteries are recycled. The lead is melted down, and the acid is either neutralized or reused. Despite all these processes, about 10 to 20% of car waste remains non-recyclable. This includes certain plastics, adhesive materials in upholstery, and textile or leather interior elements. Researchers are working on new disposal methods, such as pyrolysis, breaking materials down at high temperatures without oxygen, or using biodegradable materials for future vehicles. Today, around 12 million cars are recycled in the United States every year, making it one of the most advanced recycling industries. But back when cars first started taking over the roads, nobody really thought about what to do with them once they stopped working. Picture the early 20th century. Ford releases the legendary Model T. Cars become affordable to the masses, but what happens when they break down? In the early 1900s, old cars were often just left on the roadside or dumped in forests. Many were abandoned in backyards, slowly swallowed by weeds. Some cities even tossed them into rivers or burned them, simply because there was no system in place. Over time, scrapyards emerged, where enterprising individuals collected metal from wrecked cars, melted it down, and repurposed it. By the 1920s and 30s, metal was in high demand for construction, turning old cars into valuable resources. During World War II, the United States and Europe faced an enormous need for steel and other metals. Suddenly, junk cars became a gold mine. Governments even encouraged citizens to turn in their abandoned vehicles for scrap to produce tanks, weapons, and military equipment. By the end of the war, car recycling had become a structured industry, and businesses started opening specialized vehicle recycling plants. In the 1950s and 60s, cars became more affordable. People bought them in droves and just as quickly discarded old models. Huge car graveyards emerged, where vehicles simply rusted away, taking up massive amounts of space. Soon, environmentalists raised concerns. Oil leaks, gasoline spills, lead contamination — gasoline still contained lead back then — and other toxins were polluting the land and water. This pushed governments worldwide to implement stricter recycling regulations. By the 1970s, the first serious car recycling programs were introduced. Since the 1980s, vehicle recycling has become more systematized. Companies started using automated shredders to rapidly dismantle cars. Today, modern cars are about 80% recyclable, but manufacturers are working to push that number up by another 10%. In Japan and Europe, laws require automakers to take back their old models for recycling, encouraging the production of more eco-friendly vehicles. Recycling metal from old cars saves up to 74% of the energy compared to producing new metal. Some countries have extremely strict environmental standards: Germany, Switzerland, and Japan. In these places, before cars are crushed, they are burned in specialized facilities to remove plastic residues and other combustible materials. Sounds interesting? Absolutely. This process, called pyrolysis, happens in industrial furnaces designed for thermal decomposition. Once the vehicle fluids are drained and key components are removed, the car is placed in a high-temperature chamber. The temperature inside ranges from 800 to 1,200 degrees Fahrenheit. Materials break down without oxygen, causing plastics, adhesives, textiles, and other organic materials to evaporate, leaving behind only the metal frame. The gaseous byproducts go through advanced filtration systems to capture heavy metals and toxic compounds. The result: minimal emissions and a cleaned-out metal shell, ready for crushing or smelting. Imagine a machine that can withstand the blast of a high-explosive device, endure fire from automatic weapons, and keep rolling even with shot-through tires. This is the legendary Hummer, designed for the most dangerous missions. From operations in the Persian Gulf to modern combat zones, over 280,000 armored Hummer vehicles have become an essential part of the United States Army. How do these machines go through their testing? Which materials protect the crew? And why do they produce 70 of them per day? Let us find out. To understand why the Hummer became synonymous with invincibility, one should first look back at its history. In the 1980s, the American automobile company called A.M. General unveiled a modified Hummer that was initially developed for the civilian market. However, the troops quickly recognized its advantages for modern warfare, especially on the front lines, where soldier protection is paramount and armored vehicles became critically important for safety. A true breakthrough came after the Hummer became the main transport vehicle for the United States military during operations in the Persian Gulf at the beginning of the 1990s. Since the year 1893, over 280,000 Hummer units have been manufactured. But how can one ensure that this off-roader not only endures harsh conditions, but also provides protection in the most hazardous situations? What exactly sets the military armored Hummer apart from civilian models? Let us see how the armored components are constructed to turn these vehicles into a genuine steel shield on wheels. Military Hummer vehicles use specialized armor materials, including composite armor that combines steel plates with ceramic inserts. These materials can withstand shots from a variety of weapons, including automatic rifles and sniper rifles. Moreover, by incorporating composites, these vehicles are not only armored, but also relatively light for their size. The production rate is around 70 vehicles per day. A key structural element of the armored Hummer is the concept of plus armor. This means that multiple layers of protection are added onto the vehicle, enabling maximum defense in a wide range of combat scenarios. There are also additional design modifications, such as reinforced suspension and strengthened tires, allowing the vehicle to keep moving even if one of the tires has been damaged. Another important aspect is the strengthened floor and roof. In military Hummer vehicles, the floor is structurally protected against blasts. Special materials are used to absorb the shockwave, which reduces risk to the crew if the vehicle encounters a minefield or an explosive device. However, armor is only one part of the overall safety level. Each high-mobility multi-purpose wheeled vehicle, commonly known as the Hummer, consists of over 5,000 parts. Combat Hummer vehicles must not only be protected, they must also be real beasts capable of moving through absolutely any conditions. How is this kind of mobility achieved? In order to preserve high off-road capability and endurance, military Hummer models are equipped with a powerful diesel engine. This engine can generate substantial power that lets the vehicle easily travel through desert sands or mountainous routes, even if there is no road at all. A specialized transmission and adapted rear wheels ensure constant stability in the most extreme conditions. Many modern military Hummer vehicles integrate intelligent control systems that allow the engine and transmission to adapt to the terrain. This significantly boosts maneuverability and endurance during large-scale strategic movements. Armored versions receive steel that is half an inch thick, along with bullet-resistant glass that is 1.5 inches thick. Besides armor, electronic safety systems are vital, such as sensors that detect mines and explosive devices, along with systems designed to remain fire-resistant. They add another layer of protection for the crew, which is particularly critical in combat situations. What else is worth mentioning when talking about armored Hummer vehicles? There are several technical considerations to bear in mind. Military Hummer versions often feature specialized camouflage coatings that help them blend into the environment. This is crucial for enhancing survivability on the battlefield, where every detail can make a difference. Interestingly, the Hummer is not a static vehicle. Its design allows modifications based on mission needs. These can include additional weapon systems, medical equipment, or other specialized modules, depending on the task at hand. A military Hummer can carry up to 2,500 pounds of cargo or tow up to 7,500 pounds. Producing armored Hummer vehicles is a complex and lengthy process that demands highly skilled engineers and advanced technology. Everything starts with meticulous planning. Engineers account for every aspect, from improved mechanical components to resilience during blasts. Multiple prototypes are built, each undergoing a battery of tests. They are dropped from heights, fired upon, and examined for endurance in different conditions. Previously, AM General, the company that originally created the legendary Humvee, was in charge of production. However, in the year 2020, the license to manufacture new military vehicles was granted to Oshkosh Defense. As a result, combat Hummer vehicles are gradually being replaced by the Joint Light Tactical Vehicle, a more modern armored off-road vehicle. Therefore, military and civilian versions are produced separately, using different factories, technologies, and even materials. The body and armored panels are cut using laser or plasma machines, and then they are welded by robots and highly qualified specialists. Precision is crucial, because all seams must be airtight to enhance blast resistance. The Hummer is built on a robust steel frame, designed to withstand high loads. The chassis and engine are assembled separately, then tested for functionality. Only after that are they joined with the body. Once the main parts are put together, the vehicle is fitted with armored panels and additional protection. This stage is time-consuming because every component must be installed with the utmost precision. The interior of a military Hummer is nothing like that of a civilian vehicle. Everything is dedicated to functionality. Some models have air conditioning, which is essential in desert conditions. After assembly, the vehicle is painted with special scratch and corrosion-resistant paints. Several options are employed: desert camouflage for sandy regions, woodland or urban camouflage for the respective environments, and anti-radar coating to reduce visibility on radar systems. This is no ordinary paint. It is formulated to withstand heat, freezing temperatures, and the impact of blasts. The high-mobility multi-purpose wheeled vehicle is not produced in the same way as mass-market civilian cars. It is manufactured in relatively small batches, so fully automated production is impractical. At the same time, certain processes, such as welding and painting, are streamlined by a conveyor system for speed and consistency. Each high-mobility multi-purpose wheeled vehicle is equipped with a 396 cubic inch diesel engine that outputs 190 horsepower. This powerful diesel engine is engineered to operate under extreme conditions. The transmission is a 4-speed automatic adapted for off-road use. The vehicle has permanent 4-wheel drive and automatic differential locks. It accelerates to 37 miles per hour in approximately 17 seconds. It is slow, but speed is not the main goal for the military. For military transport, the priorities are off-road performance, reliability, and endurance. The high-mobility multi-purpose wheeled vehicle is not designed for swift maneuvers, but for traveling over any type of terrain. It has a high ground clearance of 16 inches, which allows it to clear rocks, ditches, and logs. Full-time 4-wheel drive and differential locks prevent it from getting stuck in mud or sand. The engine and fuel system are protected to withstand fire and blasts. There is minimal onboard electronics, meaning fewer things can break down in the field. It can continue moving on punctured tires. Special inserts allow driving even after the tire has been hit by a bullet. Its payload capacity allows transporting ammunition, injured personnel, and weapons ranging from machine guns to anti-missile systems. It may not be the fastest ride, but it will get you where others simply cannot go. The standard military high-mobility multi-purpose wheeled vehicle initially did not have armor, but since the year 2000, most models have received protection against small arms fire and shrapnel. Configurations vary, from soft body transport versions to the most widespread ones, capable of withstanding a high explosive device blast of up to 13 pounds. There are models with protection systems against chemical, biological, and nuclear weapons. Assembling a single high-mobility multi-purpose wheeled vehicle takes from 3 to 5 days, depending on the armor. At the AM General facility, where they build the high-mobility multi-purpose wheeled vehicle, there can be up to 3,000 workers in one workshop. However, only about 25 or 30 individuals work on assembling a specific vehicle at any given time. These include welders, mechanics, electricians, and armor specialists, each carrying out their tasks at each stage of the production line. The more complex the version, the more time and personnel are required. Before they are shipped, all high-mobility multi-purpose wheeled vehicles undergo 310 miles of test trials across off-road terrain, water, and dust. You already know how the Hummer is painted, but allow me to elaborate on the special matte paint known as chemical agent-resistant coating, which has several important properties. It does not reflect infrared light, making it harder to detect the vehicle with thermal imaging and night vision equipment. It resists chemical attacks. Its formulation makes it easier to wash off hazardous substances following chemical contamination. It withstands scratches and corrosion, enduring impacts from branches, sand, rain, sun, and aggressive liquids. The matte finish eliminates glare, which is critical for battlefield camouflage. The painting process involves multiple layers that are applied to the aluminum body and armored panels. Imagine this. By 2030, the entire world could be threatened by over 12 million short tons of spent lithium-ion batteries. But what actually happens to electric vehicles once they reach the end of their service life? It is not just simple disassembly. It is a high-technology process where even the remaining battery charge is used to power industrial facilities. Meanwhile, steel, aluminum, and plastic go right back into manufacturing, giving a new life to old automobiles. Watch until the end. You will be surprised by how efficient this recycling has become. The cost of electricity for charging is significantly lower than the cost of gasoline or diesel fuel, and the motor runs rather quietly. This, of course, increases the comfort of the ride. The most popular models are produced by Tesla, but there are many other manufacturers on the market, including Nissan, BMW, Audi, Mercedes-Benz, Volkswagen, Porsche, Rivian, Ford, General Motors, and Hyundai, which is quite a lot. However, even an electric vehicle eventually reaches the end of its service life. When the vehicle arrives at this end, it is sent for recycling. First, the car is deregistered, and then it is taken to special facilities that handle disassembly and recycling of vehicles. These can be recycling centers, auto dismantling sites, or recycling factories. Vehicles may be delivered by the owners themselves, or by dedicated services that pick up damaged or non-operational cars. Some facilities work with insurance companies or government organizations that coordinate disposal programs. When the car arrives at the site, it is initially inspected to determine which parts can be reused and which must undergo complete disposal. The site is typically an area equipped with bays or specialized zones where all processes take place. Mechanics and equipment operators work here, removing vehicle components both manually and with the help of machines. First, all technical fluids are drained. The car is placed on a special lift or in a separate drainage area. Operators use pumps or remove drain plugs to extract motor oil, transmission fluid, antifreeze, brake fluid, and fuel. The fuel is pumped out with vacuum systems to prevent fire hazards, and the motor oil is collected in containers for later recycling. After that, the disassembly of the vehicle begins. The battery is removed first and sent to a separate recycling process. There, it is tested to determine the level of remaining charge and suitability for reuse. The removal must be done carefully, as the battery contains toxic and flammable materials. This can take from 30 minutes to 60 minutes by itself. If the battery can still hold a charge, it is used in stationary energy systems, for example, to store energy from solar panels. If the battery is completely worn out, it is sent for disposal. To monitor battery condition even before disposal, Tesla, for instance, uses its own software that can remotely evaluate the remaining capacity, the level of cell degradation, and the overall condition of the vehicle's energy system. This makes it possible to determine whether the battery can be used in secondary energy applications or must be fully disassembled. Through this approach, the company reduces the number of batteries immediately sent for disposal, extending their life cycle as stationary energy storage systems for as long as possible. The recycling of Tesla electric vehicles happens in much the same way as the recycling of other electric vehicles. But there are certain specifics due to the battery design, the body materials, and the software. Tesla batteries have a complex modular structure and a high energy density, requiring additional safety measures, including a complete discharge and controlled disassembly. A full discharge of a Tesla battery is carried out at specialized recycling centers, where strict safety measures are followed to avoid the risk of fire or explosion. This is done using special equipment that gradually removes any leftover electrical energy, placing the battery into a safe state. Because lithium-ion batteries maintain a high energy density, they can still hold a substantial charge even after extended use, making the discharge process critically important prior to further recycling. According to estimates, by the end of 2030, around 12 million short tons of spent lithium-ion batteries could end up in landfills if effective recycling systems are not put in place. To discharge the battery, industrial systems of controlled power consumption are connected, gradually drawing off the remaining energy. These machines operate on the principle of creating a controlled electrical load, simulating energy consumption, where electrical energy is converted into heat that is then dissipated by active cooling systems. Another method involves connecting the battery to industrial energy storage systems, which can use the residual charge to power facilities or feed electricity back into the grid. The process occurs in a controlled environment with low humidity to minimize the risk of corrosion and unwanted chemical reactions. The temperature is maintained between 50 degrees Fahrenheit and 68 degrees Fahrenheit because higher temperatures can accelerate degradation of battery cells, while lower temperatures increase the risk of electrolyte instability. The operator oversees discharge parameters through computerized monitoring systems, which record voltage, current, and battery temperature in real time. Once the charge falls to a safe level, typically below 1% of the original capacity, the battery is considered discharged and ready for further disassembly. The battery is taken apart, separating the casing, modules, and electronics. Each module consists of thousands of lithium-ion cells that must be properly recycled to recover valuable metals. The modules are mechanically shredded in specialized installations that operate in an inert gas environment or under liquid nitrogen to prevent spontaneous combustion of any leftover active materials. The resulting shredded mass undergoes either thermal treatment or chemical solutions to remove organic components such as electrolyte and binding substances. After processing, the recovered metals are reused in the production of new batteries, and the remaining materials are disposed of in accordance with environmental standards. Toxic waste is neutralized at specialized facilities. Currently, only about 5% of lithium-ion batteries are recycled worldwide, indicating a major opportunity to improve recycling infrastructure. One key method for recovering valuable materials is hydrometallurgy. This process involves dissolving shredded elements in specialized chemical solutions that allow for the separate extraction of nickel, cobalt, lithium, and other metals. Compared to the traditional pyrometallurgical method, which uses melting at high temperatures, hydrometallurgy is more energy efficient and environmentally safe because it allows the extraction of pure metals without significant air emissions. Thus, the batteries are disassembled, casings and electronic components are recovered, and then the active electrode material is shredded. The resulting shredded mass is referred to as black powder, as it contains oxides and other metal compounds. Next, this powder is dissolved in an acidic environment, using, for instance, sulfuric or hydrochloric acid. This stage is known as acid leaching, during which the metals convert into a solution. As a result, a liquid mixture forms that contains ions of lithium, nickel, cobalt, and other elements. The next step is extraction and selective precipitation. Using reagents such as organic extractants or precipitating agents, specific metals are extracted from the solution. For example, lithium may be precipitated as lithium carbonate or lithium hydroxide, both of which are used in the production of new batteries. Nickel and cobalt can be extracted by altering the alkaline solution or by precipitation using sulfides and hydroxides. After precipitation, the metals undergo additional purification, including filtration and recrystallization. The end products, metal salts or metal oxides, are sent back into production for new battery cathode materials. The efficiency of hydrometallurgy makes it possible to recover over 90% of nickel, cobalt, and manganese, as well as up to 90% of lithium. This significantly reduces the need to mine new resources and promotes a closed-loop battery manufacturing cycle. After disassembling and processing the batteries, the electric vehicle recycling process continues. The motor and transmission are removed if they are suitable for reuse or repair. This can be done by people manually, using wrenches, jacks, and other tools, or by robotic systems that simplify the process. Wheels, radiators, electronics, and glass are also removed, and these components can be sold separately or recycled. Window glass, for instance, is recycled by shredding it into granules, which are then used in construction or to produce new automotive glass. Plastic components, such as bumpers, interior panels, and fuel tanks, are processed by shredding and later used to create new products. Only when all valuable and hazardous components have been removed from the car do they proceed to recycle the body. It may be cut into large pieces using hydraulic shears or sent directly to a shredder. Shredders reduce the metal frame to small fragments, which are then sorted by material type. Steel and aluminum are separated using magnets or electronic sensors, after which they are sent for remelting. Those parts of the vehicle that cannot be recycled may be disposed of by incineration to produce heat energy or buried at specialized landfills. The entire process can take anywhere from a few hours to several days, depending on the type of vehicle and the level of automation at the facility. However, with modern technology, the percentage of materials that can be reused is constantly rising, and it currently exceeds 3/4 of a vehicle's total mass. Imagine this. Every single year, all around the world, over 70 million automobiles are manufactured, and each one of them demands high-technology glass. From the broken flask with nitrocellulose that accidentally revealed laminated glass, to the powerful hydrophobic coatings, the history of this material is truly astonishing. Today, we are going to learn how glass becomes ultra-strong, safe, and prepared to protect us from wind, rain, and the dangers of the road. Please get ready for a journey into the realm of advanced modern technology. Thousands of short tons of glass scrap are recycled in order to create crystal clear windows for automobiles. It is not only about safety, but also about saving precious resources. And that is just the beginning. The history of automobile glass production is closely linked to the development of the automobile industry, which emerged in the late 19th century. The glass used in today's automobiles has undergone a long path of improvements that have made it safer, stronger, and more functional. When the very first automobiles began to appear, they were initially not equipped with any glass at all. The open body design offered only partial protection to passengers, while dust, wind, insects, and other hazards made traveling extremely uncomfortable. Later on, when automobiles became faster, the need for driver and passenger protection emerged. Windshields were first made from ordinary window glass, which, although it provided some degree of protection, had a serious drawback. In accidents, it would shatter into large, sharp fragments that resulted in numerous injuries. The first groundbreaking discovery in the field of automobile glass was the creation of laminated glass. This happened by chance. In 1903, a French chemist named Edouard Benedictus accidentally dropped a flask coated with nitrocellulose. The glass cracked but stayed in one piece, thanks to the thin layer of plastic. This accident inspired the scientist to develop a multi-layered glass, which later became the basis for triplex. By the 1910s, laminated glass was already being used in premium class automobiles. Its construction consisted of 2 layers of glass with a thin, transparent film in between them. In the event of impact, the glass did not scatter, and cracks remained on the film. In the 1920s, laminated glass began to be widely used in the production of windshields. Its main advantage was increased safety. Even in serious accidents, the fragments did not fly apart, but remained embedded in the polymer layer. The next stage in the evolution of automobile glass arrived in the 1930s, when the technology for making tempered glass was patented. This material was produced by heating the glass to high temperatures followed by a rapid cooling. As a result of such a process, the glass became stronger, and upon breaking, it would fracture into small pieces with dull edges, minimizing injuries. By the middle of the 20th century, tempered glass was being used for the side and rear windows of automobiles. It was less expensive to manufacture compared to triplex and provided a sufficient level of safety for those parts of the vehicle. In the 1950s and 1960s, automobile glass became even more advanced thanks to ongoing technological progress. During this time, several important changes took place. Improvement of triplex. The development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and more durable. Mass production. The automation of manufacturing processes drove down the cost of automobile glass, making it more affordable for a wide range of consumers. Coatings for sun protection. Special coatings that blocked ultraviolet rays and reduced the heating of the automobile cabin were used for the first time. One of the most significant technological breakthroughs in glass production was the invention of the float method in 1959. This technology, developed by the British company Pilkington, enabled the manufacturing of perfectly smooth glass by allowing molten glass to spread across the surface of molten tin. Through this method, the glass became more uniform, stronger, and better suited to mass production. Even today, the float method remains the foundation of automobile glass manufacturing, ensuring precise dimensions, a smooth surface, and high quality. In the second half of the 20th century, automobile glass underwent even more changes aimed at improving both safety and comfort. In the 1960s, heating filaments began to be installed in the rear window of automobiles, preventing condensation and freezing. In the 1980s, glass was introduced with special metallic coatings that reflected sunlight and reduced heat buildup inside the vehicle. Glass with ultraviolet protection. With the introduction of new technologies, automobile glass began providing virtually complete protection from harmful ultraviolet radiation. And now, we enter the modern period of automobile glass production, which we will discuss at this very moment. We shall start with the glass used in automobiles. Automobile glass is divided into several types, depending on its purpose and manufacturing technology. Windshield. This is usually multi-layered glass composed of 2 sheets of glass with a polymer film between them. This design ensures that, if damaged, the glass does not break into sharp fragments. Side and rear glass. Most often, this is tempered glass, which, upon impact, fractures into small, blunt-edged pieces that reduce the risk of injury. Panoramic roofs, or other special types of glass, often use laminated or tempered glass with specialized coatings for protection against ultraviolet radiation. The main components of glass are natural materials, which are mixed in certain proportions to achieve the desired properties. Quartz sand is the principal element in glass, giving it transparency. It must be extremely pure and contain minimal impurities. Soda is added to lower the melting temperature of glass. Lime improves the mechanical durability and chemical characteristics of glass. Additional additives. These are used to adjust color, transparency, resistance to ultraviolet light, and other properties. The raw materials are cleaned, dried, and ground to a uniform state. It is crucial to eliminate as many impurities as possible, as they can affect the quality of the glass. After preparation, the raw mixture is poured into special furnaces for melting. This stage includes a few important steps, so let us review them together. Melting temperature. To create molten glass, a temperature of about 2,732 degrees Fahrenheit is used. Throughout the melting process, the raw materials transform into a uniform, viscous liquid. Homogenization. The molten glass is stirred to distribute components evenly. This is important for preventing air bubbles or other irregularities in the finished product. The furnaces for melting glass are equipped with modern systems for temperature control and process automation, which guarantee the high quality of the final product. After melting, the molten glass proceeds to the forming stage, most commonly performed using the float method in modern manufacturing. Feeding the molten glass. The liquid glass flows from the furnace onto a bath of molten tin. Due to the high density of tin, the molten glass spreads out uniformly across its surface. Under its own weight, the glass forms a perfectly even and smooth surface. Gradually lowering the temperature makes the glass grow solid. By the time it leaves the tin bath, it is ready for further processing. The float method allows the production of glass sheets with precise geometric parameters and a very high-quality finish. Once it is cooled, the sheets of glass are cut to the sizes required for automobile manufacturing. Automated cutting machines ensure accuracy, and to prevent chips or cracks, the edges of the glass are polished. Every sheet is checked for defects, such as microcracks, bubbles, or other damage. Next, to ensure the strength and safety of automobile glass, it undergoes the process of tempering. The glass is heated to a temperature of around 1,112 degrees Fahrenheit. Then the surface is quickly cooled by air jets, while the inner layers cool more slowly. As a result, stress is created, which greatly increases impact resistance. Tempered glass, when broken, shatters into small, safer fragments, minimizing the risk of injuries. After that, for the windshield, a triplex construction is used, which is a combination of glass and polymer film. Its fabrication involves several steps. Layer bonding. A polymer film is placed between 2 sheets of glass. The construction is placed into a vacuum press to remove air bubbles. Then the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure, ensuring a strong bond between the layers. Triplex has high impact resistance, and if damaged, the fragments stay attached to the polymer film, thus providing safety for the driver and passengers. Afterward, to enhance the properties of automobile glass, various coatings are applied. Anti-glare coatings. Reduce glare from the sun or from other vehicles' headlights. Ultraviolet protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings. Allow water to bead and roll off the glass surface. Heating elements. Thin heating filaments can be embedded in the windshield, making it easier to remove ice or condensation. To achieve the required shape, special thermoforming equipment is employed. The glass is heated to a temperature at which it becomes pliable, and it is then molded according to specified parameters. And here we arrive at the final stage. During this stage, each piece undergoes a thorough inspection. The transparency is tested, and any defects are identified. Next, the glass is tested for impact resistance and durability under load, compliance with standards, the accuracy of dimensions, the shape, and other parameters are verified. Then the finished automobile glass is packaged in a manner that prevents damage during transportation. It is delivered to automobile factories or service centers, where it is installed in vehicles. The production of automobile glass is a high-technology process that brings together physics, chemistry, and engineering. Thanks to advanced technologies and strict quality control standards, automobile glass ensures safety, comfort, and longevity. And just imagine how many stages automobile glass must go through so that we can watch over road safety and admire wonderful vistas along the way. I find it remarkable. Do you also think so? Imagine a motor that can spin up to 23,000 revolutions per minute and produce a level of power that in the past only Formula 1 race cars could achieve. Now picture that motor installed in your Tesla. How did Tesla manage to create such revolutionary electric motors that have made its cars the fastest in the world? From asynchronous motors to the innovative plaid carbon-wrapped versions, today we will dive into the world of technology that is reshaping the automotive industry forever. Are you ready to discover what is inside the most powerful electric motors of our time? Then let us get going. Asynchronous or induction motors were installed on Tesla Model S and Tesla Model X in their earlier versions. Synchronous motors with permanent magnets are used in Tesla Model 3, Tesla Model Y, and later versions of Model S and Model X. Wound rotor motors represent an enhanced technology that combines the benefits of the previous types. Each of these motors has its own unique aspects in manufacturing. Before initiating production, Tesla engineers design the motor using modern modeling software. The design process considers the materials for magnets and windings, the shape of the rotor and stator for maximum efficiency, the cooling system to prevent overheating, the balance of weight, and the positioning of the motor in the car. After completing digital modeling, prototypes are produced and tested under laboratory conditions. Now let us move on to the stage that focuses on the key components. The first component is the stator. It is the heart of the electric motor and the stationary part of the motor, containing copper wire windings. The stator core is made of many thin layers of electrical steel, which helps reduce energy losses from eddy currents. These steel sheets are cut by laser cutting or stamping. The sheets are assembled together and pressed into the form of the stator. The next step is the coil winding process. Automated winding is utilized, along with a precise calculation of the number of turns. In order to boost efficiency, hollow copper wires with coolant flowing inside are used. After the winding, vacuum impregnation with varnish takes place to protect the windings from overheating and damage. We then proceed to the stator assembly stage. The windings are connected to electrical contacts. Temperature sensors are installed to monitor heating. The completed stator is subjected to quality control and testing. The rotor is the moving part of the motor. Tesla uses two types of rotors. An asynchronous rotor with a squirrel cage is employed in induction motors. It is made of aluminum or copper by casting the metal into a mold. A rotor with permanent magnets is used in Tesla's synchronous motors. It contains magnets based on rare earth metals, creating a strong magnetic field. As with the stator, a multi-layer steel structure is used for manufacturing the rotor. The steel sheets are cut and either glued or pressed together into the shape of the rotor. Neodymium magnets are inserted into the rotor body. The magnets are secured by adhesive or mechanical fasteners so that they can withstand rotational speeds of up to 20,000 revolutions per minute. Because the rotor spins at high velocity, perfect balancing is essential to avoid vibrations. The rotor is tested on specialized equipment that automatically adds or removes material to adjust the balance. The next stage is motor cooling. Tesla employs liquid cooling for its electric motors. Coolant circulates through channels in the motor housing, carrying away excess heat. This enables the motor to function at high power levels. The rotor is mounted on bearings for minimal friction. The stator and rotor are placed inside the motor housing. All components are connected according to the design. A controller operates the motor by regulating power and rotational speed. Metal oxide semiconductor. Field effect transistors, or insulated gate bipolar transistors, are employed to convert electric current. We now move on to the final step, which involves filling the system with cold fluid. The coolant is introduced into the cooling system and checked carefully for leaks. Following assembly, every motor undergoes an extensive battery of tests. A no-load test verifies smooth rotation. A load test evaluates efficiency and energy consumption. A thermal test stresses the motor under maximum loads. A noise test measures noise and vibration. Only after passing all these tests successfully does the motor proceed to the production of Tesla vehicles. Manufacturing Tesla's electric motors is a high-technology process that integrates advanced engineering approaches, automated manufacturing, and sophisticated testing methods. Tesla continually improves its motors, making them more efficient, more compact, and more powerful. This technology lets Tesla produce electric vehicles that outdo the competition in power, range, and reliability. The story of how Tesla developed electric motors for its cars is one of innovative technology, risk-taking, and the relentless efforts of engineers. It all started with an ambitious plan to revolutionize the automotive industry, and although initially the company did not produce its own motors, it ultimately became a leader in this domain. Tesla Motors was founded in the year 2003 by a group of engineers, which included Martin Eberhard, Mark Tarpenning, Ian Wright, Jeffrey Brian Straubel, and the future chief of the company, Elon Musk. The main vision was to create an entirely electric car capable of competing with conventional gasoline-powered vehicles. At that time, electric vehicles did exist, but they were slow and inefficient. That was when the Tesla team decided to utilize an asynchronous electric motor, originally patented by Nikola Tesla in the year 1888. Tesla's first electric motor was developed using technology from a company named AC Propulsion, which was creating high-powered electric motors for electric car prototypes. Tesla established a licensing deal with AC Propulsion and adapted its technology for its first model, the Tesla Roadster of the year 2008. This was a three-phase asynchronous motor featuring a rotating magnetic field. It was manufactured with an aluminum rotor, which provided excellent efficiency. The maximum output was 248 horsepower, enabling the Roadster to accelerate to 61 miles per hour in 3 9/10 seconds. Despite the success of this first vehicle, Tesla encountered difficulties with component supplies. The motors were made at external factories, and quality control was lacking. This pushed the company to consider setting up its own production lines. Transitioning to in-house production took place from the year 2010 to the year 2012. When Tesla started developing the Tesla Model S, it became clear that the company needed to manufacture its own electric motors. There were multiple reasons for this. The first reason was cost, since sourcing motors from external suppliers was expensive. Tesla also wanted a highly efficient motor designed to meet its specific requirements, meaning the design had to be optimized. Quality control was the third reason, because in-house production allowed the company to oversee every aspect of manufacturing. In the year 2010, Tesla purchased a plant in Fremont, California, previously owned by General Motors and Toyota. This was a pivotal milestone in scaling up production. In the year 2012, the Tesla Model S became the company's first vehicle to use Tesla's in-house electric motor. It was more powerful and more efficient than the previous generation's motors. The Tesla Model S motor of the year 2012 represented a breakthrough in technology. It was created using asynchronous induction motor principles, with a copper rotor instead of the aluminum rotor that was in the Roadster. The copper rotor raised efficiency and diminished heat losses. The performance version delivered 416 horsepower, enabling acceleration to 61 miles per hour in 4 4/10 seconds. This model drew global attention, and Tesla expanded rapidly thereafter. Let us examine the newer generations of motors from the year 2017 to the year 2020. Although asynchronous motors remained efficient, Tesla's engineers began exploring new motor designs. In the year 2017, during the development of Tesla Model 3, the company chose to adopt synchronous motors with permanent magnets. The Tesla Model 3 motor, starting in the year 2017, is a synchronous motor with permanent magnets. This made the motor smaller, lighter, and more efficient. Neodymium magnets helped reduce energy consumption. The refined cooling system enhanced reliability. This motor became standard in Tesla Model 3 and Tesla Model Y. However, Tesla did not stop using asynchronous motors and continued installing them on the front axle of Tesla Model S and Tesla Model X for dual motor versions. Tesla pushed forward and introduced its plaid carbon-wrapped motor technology, which premiered in the year 2021 in Tesla Model S Plaid. Plaid carbon-wrapped motor is a revolutionary solution. It utilizes a carbon wrapping on the rotor, enabling incredibly high speeds of up to 23,000 revolutions per minute. An improved cooling system endures extreme stresses. The Tesla Model S Plaid can accelerate to 61 miles per hour in only 1 99/100th seconds, making it the fastest production electric car in the world. This technology was entirely developed by Tesla's engineering team and is unmatched by any competitors. Manufacturing electric motors for Tesla cars is a sophisticated and advanced process encompassing pioneering research, modern simulation, automated assembly, and meticulous testing. Tesla gradually evolved from employing asynchronous motors in its early models to integrating state-of-the-art synchronous motors with permanent magnets and the revolutionary plaid carbon-wrapped motor. Through continuous enhancements of its technology, Tesla has produced motors that combine outstanding efficiency, power, and compactness. This enables its electric vehicles to surpass competing models in acceleration, energy consumption, and reliability. Tesla's decision to make electric motors in-house allowed the company to manage quality, reduce costs, and refine designs, proving to be instrumental in its expansion. The unwavering drive toward innovation and the pursuit of new advancements solidify Tesla's role as a leader in electric transportation, shaping the future of the automotive industry. Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress. So there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating, As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty.